So in 3.6b, we're going to go back to optimization problems and do a few more problems. So this first problem is similar to one we did before. We have a cylindrical can with no lid. It is made to hold 216 cubic centimeters of liquid. We're being asked to find the dimensions. Meaning the radius and height of the cylinder. That will minimize the cost of the materials that are used to make the can. All right, step one, we always want to draw a picture out. We need to draw our picture and label it. So we're going to have a sketch here of a cylinder. It is open at the top, or no lid. Then we have our two variables here. We have the radius and we have the height. All right, so let's go ahead and talk about the given information for the known equation. So the known equation is going to be the surface area here, or the volume, since this is cubic centimeters. So volume of a cylinder is area of the base times the height. So the base is a circle. Area of the base is pi times the radius squared times our height. All right, second is going to be our unknown. This is going to be what we want to solve for. What are they asking us to find? So finding the dimensions, we want to minimize the cost. Okay, so that's going to be our secondary equation there. Whatever you want to maximize or minimize. Now, they didn't tell us anything about what the cost of the materials would be. The cost of the materials is going to be used to make the side of the can and the base of the can. So the thing we want to minimize then is the surface area. So we're going to write out what the surface area is here. So the base area, pi r squared, we already know that one, plus the surface area of the side. So we know that if we were to take a cylinder, take off the top and the bottom, we cut down the side and we unroll it, we would end up with a rectangle. So this is the siding of the can. Right. So that siding has a height of h still. The length of the can here is what we unrolled. So it's just the length around the rim of the can, and that's going to be our circumference. Circumference is 2 pi times the radius. So the area of the side is 2 pi r times h. All right. The third thing we're going to do is whenever we want to find the minimum of something, we want to take its derivative since we're looking for its critical numbers. So before we can take the derivative of the surface area, remember that it must all be in terms of the same variable. So we need all the same variable here first. So that means we either need to have all R's or all H's. So easier just to replace one H. So we're going to go back up here and use this formula. We're going to solve for H. So 216 divided by pi r squared, and we'll substitute that in here. Now that we're all in terms of the same variable, we can simplify this. So 1r reduces, pi reduces, 2 times 216, we're going to get 432 over r. So my surface area has now been simplified. So I want to minimize the cost, and the cost is simply based on the surface area. So this, we're ready to go ahead and do step 3, which is take the derivative, set it to 0, and find our critical numbers. So over here, we want to find critical numbers of cost, which is surface area. So our function we're working with here, pi r squared plus 432 over r, or r to the negative 1. We'll take our derivative. Okay, so we end up with 2 pi r minus 432 r to the power negative 2, so over r squared. And in finding critical numbers, remember we set this equal to 0 and solve. So I'll add 432 over r squared to the right, multiply r squared over to the left, and we'll get r cubed is 216 divided by pi. So that would tell me that r must be, well, the cube root of 216 over the cube root of pi. And that's measured in centimeters. So remember, we're asked to find the dimensions that minimize the cost. The cost is the surface area, so we're minimizing the surface area or finding the critical numbers of the surface area. And in finding the dimensions, we have found the radius. So this is one of my answers. Now I just need the height of the cylinder. So we're going to go back into our problem here, where we had our known volume, 216 equals pi r squared times h, or h is 216 over pi r squared. So I'm going to plug r right back into this equation here and solve for h. So plugging that value in here, my last step here is to find h. So this doesn't look very pretty, but we can still work with it. We've got 216 over pi, and then 6 squared is 36. And this, I'll just rewrite this as pi to the power 2/3. Okay, so we can simplify 216 over 36 down to 6. And then on the bottom here, pi over pi to the 2/3 will reduce to pi to the 1/3. And so I also get 6 over the cube root of pi centimeters. So there's our height. We're going to do one more problem here. Number 2 is just slightly different from number 1. We'll start with a rectangular storage container. With an open top. Has a volume of 14 cubic meters. The length of its base is twice the width. Here's where it gets a little different. Material used for the base is $11 per square meter. And for the sides, the cost is $8 per square meter. So already what's making this difference is my surface area is the cost. However, materials cost different amounts here. So it's going to make a difference in this problem. And we want to go ahead and find the total cost for the cheapest container. So we are still trying to minimize surface area because we want to make it as cheap as we can. We don't want a whole lot of surface area. Okay, so it's still minimizing here. Cheapest container. Minimize cost. But this time the cost is not just surface area, it's price per surface area. So I have to take these two values into account as we do the problem. So we'll start like normal and make our sketch. Okay, so a rectangular storage container, open top, so no lid. The length of the base is twice the width. That looks pretty good. So once again, open here, lid. Okay. So again, the length of the base is twice the width. So if I call this side X, we're going to call this side 2X. And then the height, well, we weren't told the height, so we'll just call it H or Y if you want. Now, we're going to write our two equations. So we'll start with the known equation. And in this problem, the known information, again, is the volume. Volume is 14 cubic meters. So volume, we have 14 is equal to, and volume is length times width times height. So I have 2x squared times h. Next up is the unknown, or what we're trying to find, or what we're trying to minimize. So in this case, we are trying to minimize cost. This is where it gets a little tricky, since the cost is based on these two prices per side or base. So the cost here is going to be $8 for each square meter of side material. So let's go back and look at our side material. So the front and the back both measure x by h. So I have two sides of x. The right and left sides measure 2x by h. So that's going to be 4xh. Okay, and then we're told that for this surface area, it's $8. For the base, Okay, our surface area is x by 2x, so 2x squared. Remember, there is no top, so it's just the base itself. And this is going to be $11 per square meter. So I'm just multiplying these values together to get my total cost. So the sides, this is a total of 6xh times 8 is 48xh and 22x squared. So that's my cost function, or my cost formula. This is what I want to minimize here. Notice it's not just surface area, it's price per surface area, price per surface area. So because the costs were actual values this time, I had to include them in my function. Otherwise, we're not going to get the right answer. So this is the function we want to minimize or find its critical numbers. Before I can do that, it always has to be in terms of one variable. So here's where we're going to make a substitution. I'm going to go back to my previous known formula. This is what the known formula is going to help us with. And each will be easy enough to solve for. So if I solve for 8 here, I get 14 over 2x squared, or 7 over x squared. And we'll just substitute that right in here for h. Now my cost is 48x times h, 7 over x squared, plus 22x squared. Right. We'll simplify that. So we have 48 times 7 is going to give us 336 over x plus 22x squared. So we'll take this function over here. Remember, to find critical numbers, we want to take our derivative. So I'll rewrite that as 336 times x to the negative 1 plus 22x squared. So our derivative, negative 336, x to the negative 2, which is over x squared, plus 44x, does it equal 0. So solving here, I'll add the 336 over x squared to the right, multiply x squared back over to the left, I get x cubed is equal to, not a very nice number, so on, and then the cube root of this number is going to give us 1.969. All right, so this is the value that will minimize the cost. So this is the length of the base and double the width. And then we could plug that back in and we could find the height. But none of these things are what the problem asked us to find. The problem asked us to find the total cost. So right back here and find the total cost. So my cost function, all in terms of x, was right here at the bottom where we left off. So what I'm going to do is take this x value, plug it in here. Notice I don't need to go back and find h as well. I just need x. So I'll plug this value in here and get my cost. So this comes out to 255.94. And there's the cost of the container.